So my talk is about a data collection system that we built at Alert Logic and the lessons that we learned along the way. So before I describe what our system does, and by the way, how many of you have written applications in Erlang? Almost everyone. So, but for those who do not have experience with Erlang and the rest of actually the audience, if you have any questions, feel free to interrupt me at any time. So, before I describe the actual, and my talk comes in two parts. In the first part, I will describe the system, what it does, and our architectural approach. And in the second part, I will go over the list of problems that we encountered while building, testing, and testing the system. So, so let me start with some numbers. So these are numbers from last year. And so in the first row, you can see the number of logs Alert Logic collects every day from various servers, and on the and the number of tweets Twitter receives. So the second row corresponds to the actual data volume. So what the first row means in actual data volume. And in the third row, and I thought this number is really, really interesting in Twitter, like their servers actually generate 100 terabytes of logs a day. So they shared this number last year in one of the talks at Strange Loop. And the number of logs we generate, our servers generate, is not that interesting. So which means that our operational footprint is low. And to be honest, it's not like a fair comparison. Like these companies are completely different. So the things that Twitter does with its server logs is really, really interesting. And they have like a completely separate team that all it does, it supports like this massive Hadoop cluster. They do lots of analysis there. So what essentially Twitter does is that it takes some fair number of human-generated messages, then distribute it to a massive audience, and does a lot of analysis, and that's probably contributes to that 100 terabytes a day of server logs. Alert Logic, on the other hand, collects machine-generated data, and then it runs. Then we run some analysis and present the results and the collected logs to the users and security analysts in summarized, filtered, or other meaningful ways. And the type of analysis that we run is mostly related to network security and compliance. So this is what our system looks like as of last year. So Alert Logic has a product called Log Manager. Log Manager is a hosted log management solution. At the top, you see a 100,000 hosts from which we collect data today, well, last year. And we do it via appliances. And it works this way. Customer signs up. We send them an appliance. He racks it up, configures log collection through our web UI, and then appliances start collecting data from remote hosts. And once they collect, they send data to our backend, to our data center. Then we do a bunch of stuff in the data center, and we finally expose the collected logs and some analysis results, reports, and other stuff to the user through the web interface. So the problem with that system is actually here in appliances. The problem with appliances is that appliance is a physical server. It's a small server, but there's still some cost associated with deploying it and managing it. And they're deployed all over the place. We have customers like everywhere. And this piece of hardware can break down. And in order to account for that, you need to either keep a provisioned spare or send a replacement really quickly, or start thinking about doing highly available appliances, which is doable. It's not a rocket science, but so we had to do something about that. And then Rackspace, one of our largest partners, start telling us, hey, your appliances take too much of our rack space. Can you do better? So at this point, and of course, we had to account for product and company growth. So in the new system, we were looking at collecting data from over 1 million hosts, different hosts. And going back a little bit, just to describe the kind of logs we collect, for the most part, these are server logs. So we collect syslogs, we collect logs from Windows boxes, and also logs, what we call flat file logs, such as Apache, MySQL, IIS, and everything that's basically written to a file and can be like, and rotated and not rotated in some way. and those hosts, some of them, go ahead.
Yes, I'm sorry. So you have, like, you were collecting logs from hundreds of thousands of machines, right?
That's correct.
Over the year, you've collected only 5 terabytes over 1 year?
It's a daily number.
Oh, daily storage. Okay.
I think the slide says that. Yeah, it's daily numbers.
Sorry about that.
Oh, that's fine. So if anyone has any questions about the numbers, I'll be happy to clarify. So, and some of these hosts are real servers, like web servers or database servers or domain controllers. Some of them are, and they send a lot of logs. And some of them are like point-of-sale terminals running some ancient Windows version behind like really slow links. So it's a kind of, it's not a typical data center environment. So collecting logs from them. And some hosts go up and down, like they don't have permanent internet connection. They're located somewhere in like oil rigs. So collecting data from collecting logs from them is actually a fairly challenging problem. And doing it at scale, of course, is even more challenging and reliably. So in the new system, we're looking at collecting logs from over 1 million of hosts. And we also had to solve the appliance problem. And it came down to 2 things. So we introduced agents as a primary product deployment method. And an agent is a program that you install as a software package that you install on your host, and it collects logs just from that host. And we also had to simplify our appliances a lot to make them more manageable. So the hosts at the top, they do not go away. So we collect them today as we were collecting from them yesterday. So remote collection is still very important use case. But we wanted to offer more flexible deployments and solve some of the management problems that we had. So those are marked, new appliances are marked as A prime, and agents are in the yellow ovals marked as H prime. But the rest of the system is pretty much the same. So since the remote collection stays pretty much the same, I'm going to focus on the new way dealing with agents and our new appliances. So zooming in, I need to tell a little bit about what we do once we receive the logs. Well, first of all, we need to collect them. And after we collect them, we store them, run some analysis, run reports, make the logs searchable, generate alerts if they're configured, and finally expose all of that stuff through the web UI. So if we look inside the new appliances and the hosts on which we install new agents, the software that they're actually structured as a set of programs written in C++. And one program, for example, handles syslog collection. Another program handles Windows event log collection. The third one, flat file collection. And the fourth program supervises the first 3. So, and we call them clients. And the reason we call them clients is that each program, regardless of where it runs, communicates with the backend directly. So they don't actually coordinate between each other. And we try to keep them as simple as possible. So all the actual coordination happens in the backend. So they just perform the log collection function. Another interesting thing is that those clients that run on a host on which we install an agent or inside the appliance is essentially the same programs. So, and it's almost the same. It's the same code. In the case of appliances, they perform remote collection function, which means if you want to collect from a remote Windows host, those programs reach out to a remote Windows host and collect logs from them. If it's an agent, they collect from the local host. And they speak exactly the same. Remote collectors and local collectors speak exactly the same protocol to the backend. and they're also like very, very simple. They're statically linked. We also built some management functions to simplify our job. For example, we can upgrade them remotely. So we have a function built in special clients that allows us to upgrade software versions or downgrade individually or sets of agents and sets of appliances at once with a push of a button. So if we look at the backend, it is structured in 3 layers. And the backend, I'm talking about collection system mainly here. And I'll focus on the collection system specifically. So the collection system includes a load balancer, and clients talk through that load balancer to the what we call collection controller. Those are actual nodes, and load balancing and persistent queue are functions. And finally, the final goal is to offload all the collected logs to the persistent queue. So this is what our system essentially does. Now, knowing that all those clients are actual small programs that talk to the backend independently, we can like simplify this diagram. And for the purpose of this presentation and architectural, overview, treat those clients independently. So, the original program then transforms into having hundreds of thousand clients running somewhere all over the internet that talk through the load balancer to the collection nodes, collector controllers, and finally their logs end up in the persistent queue. And of course, this picture wouldn't be fully complete if I didn't specify the protocol. So the clients communicate over HTTPS with client-side SSL certificates, and we heavily rely on sticky sessions. That's a pretty conventional term for specifying that all those clients maintain association with a specific backend node, specific controller nodes. And if you forget for a second that these are called collection controllers, and there's some like weirdness, a persistent queue here, this looks like a typical web application architecture. So what's different, though, is the fact that unlike in a typical web application, our clients send in us lots of data. And in the typical web application, clients would send small requests and receive data back. So it's kind of the opposite picture. Another thing that makes it different is that the collection controllers, they basically receive a portion of collection logs. This is the brain of the system, by the way. We keep clients very simple, and the collection controllers, they decide what to collect, when, from which host, at each interval, and what to do with collected data. So, and normally when they receive a new portion of collected logs, they apply a little bit of transformation, mostly attribute expansion, and call a couple of services, and finally write it to a persistent queue. So while they're doing that, the data, the collected portion, sits in memory. So and it stays there until this final step of data processing finishes. And that's also, and not only collection controllers, but some of the stuff in the load balancer does the same. And we optimize our data collection system for collecting as less often as possible, and we try to collect data in chunks. That helps us to, so we buffer logs a little bit on the clients, and we do it specially so that we know that like larger buffers of logs compress better, and we transfer data compressed. And it also helps us to minimize the request rate. So essentially that helps to keep the volume, the request rate here and here lower. And it helps with some of the transactional stuff that we do here when processing logs. So, and I would claim that this problem is actually is much harder than a problem a typical web application needs to solve. Basically, you're dealing with lots of data that's coming your way, and you need to do it, to handle it in a certain time, and do it very efficiently. So we try to do as less operations, data processing here as possible to keep that efficient. So, and if you look notice the number 3 next to the collection, it's the actual number that we have today in production. So there's our literally 4 core virtual machines. And if you look at the original diagram, we had 1,000 appliances. And the collector controller function used to run on appliances in the old system. And now we brought it down to 3 collectors node. And the collectors controllers, they're implemented in Erlang. And the similar type of Erlang program used to run on our appliances. So that's the idea behind the name of the talk. So how we took the program that ran on 1,000 nodes and got it to run on only 3 or a handful of nodes. And we can do it very, very efficiently. We learned to do it very efficiently. So if we look inside the collector controller nodes, and it's a very, that's an Erlang application. And inside that Erlang application, for each thousands of clients, we have a matching Erlang process running. And it's a long-running Erlang process, and HTTPS requests routed through the load balancer from the clients eventually get delivered to this Erlang process in a form of gen server call. And then they do all the processes. And and all those like 20, 40,000 Erlang processes basically do their work simultaneously, all at the same time. And this is exactly the use case that Erlang was built for. It's a fairly typical application architecture scenario in telecom. So when you have lots of processes, small processes that doing a little bit of work, and they all do it all the same concurrently. And Erlang really shines at that. So basically, you don't have to think how to map all this, like thousands, tens of thousands of concurrent things happening to your handful of CPU cores. The Erlang VM does it really well, and it does it with soft real-time guarantees. So basically, it guarantees that they all keep moving slowly if they're bottleneck on some like CPU resource. Go ahead. That's a good question. I actually forgot to mention that. So the load balancer, we went back and forth on various load balancer options. And we quickly found out that Erlang is not Erlang SSL implementation is not very efficient. So we basically decided not to terminate SSL in Erlang. We're seriously bottlenecked on CPU. So, and we right now, and it's going to be changing, I'm pretty sure, but right now we're using a combination of HA proxy for SSL termination, and we have a custom-built HTTP 1.1 reverse proxy written in Erlang for doing some of the stuff that we need. So one particular thing that we need in a load balancer is maintaining those sticky sessions and also dynamic reconfiguration. So we need to be able to rebalance load, basically take some of the clients from one node and move them to another node. We need to have dynamic blocking, like if some client starts misbehaving or something else like happening that we want to prevent, like down the stack, we can quickly block it at the load balancer level without, changing HA proxy configs or anything like that. So we have a separate system built for that. It's 4 cores VM running on VMware, vSphere, whatever. So, and we have 3 of them, and we know that we can. So remember I was talking that hosts, like those clients generate load at different rate. So some of them will be like constantly spinning and sending new portions of logs, and some of them we will reach out to them like every 5 minutes or so. So it's a little bit hard to predict the exact load on those controller nodes. So because right now we're in the process of migrating production customers from old to the new system. So this system is not fully loaded yet. But during load testing, after we spent a couple of months bidding our system, we gotten pretty confident about that setup. And this collector nodes, the layer of collector nodes, they provide basically a horizontal scalability level, so we can add any number of them as we grow. They don't talk to each other. They are bottlenecked only on some of the external services and on the persistent queue, and also on CPU and memory if it fills up. So we all right, so these are some of the services that those controller processes need to call while they process portions of collected logs. So we update collection statistics, and we have kind of like a commit event, because we need to, our product is used for security and compliance, and we need to collect logs reliably, so we cannot lose logs. And after we finish the collection cycles, we write a special indication about like the position at which we finished collecting them, and we store it permanently. So this is one of the operations. And of course, we have about 10 different services that those collection controllers call like configuration database and other stuff, some operational tools. But we know that in real life scenario, we can support about 1,000 requests going between clients and collection controllers per core. So as I said, we were optimizing for doing very little work in the collection controllers. And we keep hitting bottlenecks, of course.
What are you using for the persistence?
For the use case that I described, committing the collection state, we use React. And that's a purely key value type of operation. So we store it by key and we load it back by key. For example, if a collection controller node gets restarted. And it actually works really well. So if you know React and what it can do in terms of key value, it's like the best. No. And the persistent queue is also custom built. It's not React. React is used, and a bunch of Erlang is used in all our other systems, like storage offline data processing, interactive querying, interactive searches. But I'm not going to be able to talk about that today. So React is used in some other parts of the system, but this case is very, very simple, this use case. So, and it's interesting. So, and we couldn't see that while we were like re-engineering the system. We couldn't really answer that question. So, what changes when you actually bring a program that runs on 1,000 nodes and get to run it on a like 3 or 5? Well, it turns out like everything changes, and some of the things are obvious. Like it's just a lot more work. In terms of request rate, data volume per your server, per your node, number of open connections, of course, the number of processes per VM goes back. And also you start seeing some things that you don't normally see in a not so loaded environment. Like your failure rate and all those side effects that hang off of it goes up, and some bugs get exposed, race conditions, and even memory leaks that you would otherwise wouldn't have noticed. And another kind of problem, it's more of an operational problem, arises from the fact that now all the customers and all types of clients generating that have different load patterns, they basically connected to the same set of nodes. And that means a misbehaving client can affect others. You cannot easily say what's going inside of your Erlang VM because, as I said, the load is not uniform. Like one host can generate a gigabyte logs an hour, and another one can hardly generate any, and they have completely different like performance footprint. It's becoming harder to troubleshoot things in like what's going on during like processing of collection response. And with appliances running, one or a couple of appliances running per customer, well, if something happens, like your appliance goes down or some network connectivity issue comes up, like other customers will notice. If anything happens to that environment, well, everybody gets affected. So you need to account for that. And it wasn't, and you kind of think about all these problems in the beginning, but then it takes a lot more time than you think to build systems to work with them. And then, of course, you need so in order to deal with some of these problems, you absolutely need application monitoring with several thousand requests per second. You can't get much value from logs, from looking at logs and monitoring your server logs. You need to, if something goes bad, you need to react fast. And for this reason, you need interactive dashboards and monitoring, and you need to be able to visualize your application behavior from different angles. I'm going to show you some examples and how it was very helpful. Like, it's super critical. Like, you cannot do anything without that. We use Graphite and the Erlang library to offload many application metrics that we collect to Graphite and then plot them. So now, as I said, in the second part of the talk, I will go through the list of problems that we actually experienced during load testing and explain what the problem was and the resolution step and typical resolution scenario. And some of these problems are, for the most part, they're going to be specific to Erlang. So the first problem, once we started loading the system, we implemented, kind of ran through a little bit of integration testing, making sure that the system more or less works. And then we turned on load, and we saw like pretty much very fast death of the Erlang VM because it ran out of memory. And if you, just to remind you, so those controller processes running in Erlang VM, they handle quite a bit of data. So data comes in, they need to transform it, write it to persistent queue, and this means that they generate a lot of garbage. And it turns out, in a loaded environment, Erlang garbage collector, which is per heap, basically when they generate garbage, they generate it on their own heap, and also part of it in a binary heap. But most of the messages that we collect, they're represented as Erlang binaries. Erlang binaries is essentially a mutable array of bytes. And basically, what we've learned is that by default, garbage collection in a loaded system may not keep up with the data generation rate. So you create more garbage and don't collect it fast enough. And the solution, our solution to that was very simple. So after each interaction between the client and the collector process, we just we force garbage collection on that controller process. And it immediately solved the problem, and we measured the overhead. It was good.
For every message from the client?
Yes. So, and we could have applied it selectively, but it worked so well, so we never, it's one line change, right? We've never gotten to like optimizing it. We measured the overhead on a not so loaded system. It was like within single-digit %. So we never actually had to do anything about that. And it's probably due to the fact that we do so little, try to do so little when handling requests. So we don't generate a lot of garbage. And most of our garbage is binary data that comes from collected logs. And it can be apparently collected very easily. So those heaps, process heaps can be rolled up very, very quickly. That was easy. So the second one, well, that was actually tricky, and you need to know more of Erlang in order to solve it. So the problem was that you turn on the load, you wait for a while, you remove the load, so you turn on the load, memory usage goes up, you remove the load, memory usage goes down, but not all the way down, which means that during that time, something got stuck somewhere. And as we were running tens of thousands of clients, it kind of built up. So you start with simple things, right? You just try to garbage collect all the processes in the system. And if you remember, we already do that for collection controllers. But we have a whole lot of other Erlang processes running, like we have connection pools, we have caches, and everything else to help to speed up our application. So you do this, it helps a little bit, but doesn't really solve the problem. So the data is still there. And then you start typing those crazy queries, trying to find where your sub-binaries are. Does anyone not know what a sub-binary in Erlang means? Okay, so as I said, there is a type, built-in type called binary, which is an immutable array of bytes, and you can take a slice of it. Basically a slice, and it's called a sub-binary. It's represented as a starting position and the length of the slice. And the slice is treated as binary as well. It's handled by the language and the runtime transparently. Normally you don't have to care about that, and it's much cheaper to pass it around this small slice rather than do copying on larger binaries, for example, like create more objects and create more garbage. And Erlang offers a lot of troubleshooting capabilities. In that sense, Erlang is fantastic. And I'll quickly go over what this crazy things, and those crazy things you type in a Erlang shell, remote shell. So you log into the node and you start typing all those commands. And it's not that you type it all at once. Usually you try to do simple things, and then it gets more and more complicated because you're trying to narrow down the problem. And this function goes over the list of processes. and it extracts information of binary references by calling this process info function and doing some actual work to extract that information about that. And then it takes, it's got to sort it somewhere by, takes a sublist of 5. Oh, there's the sort. So it fetches, basically sorts the results, trying to find the top users of binary, top holders of binary references out of all processes. And that takes five of them. Here's list, sublist. So, and as a result, you see things like that. And for those who are not familiar with Erlang, that's a typical notation for supervisors. So you see that some binary, like 500 megabytes is sitting in some supervisor. Supervisor is never meant to like hold any data, so it's absolutely crazy. And there's a popular open source package called gproc that also doesn't do much, and yet it references like significant volume of data. So, and you kind of keep thinking about that and then start killing parts of your supervisor tree, because after you killed this, it didn't help. Like the memory went down usage, but it's still like higher than it used to be that it was before the test. Then you start killing parts of your supervision tree, like parts of your application, and finally, like you win. So all the memory goes back to when it was. And it turns out the problem was related to subbinaries. So one thing that I didn't tell you is that we don't use raw HTTP when we're communicating with between clients and the backend. We have an RPC layer there, and RPC layer allow us to basically tell clients to execute some commands, and then come back, and then they come back with responses. And we use protocol buffers. It's a popular package. Popular serialization format, open source by Google protocol buffers, to represent our like RPC protocol headers. And the library, which I happen to be the author of, when it parses those HTTP responses, RPC responses, it creates a lot of small subbinaries. Because it's a binary blob, you try to turn it in a structured Erlang representation, and it creates a lot of subbinaries. And while doing that, it doesn't copy them. And parts of those subbinaries used as like process identification. So we use them in process identifiers registered with gproc, parts of supervision tree, child specs, child parameters, start parameters, and that leads to. They also ends up, and that leads to those subbinaries like sitting all over the place in our application and referencing fairly large binaries that correspond to the original blobs that we receive from the client. And it turns out those subbinaries can end up anywhere. They can be in process heaps, then they can be in ETS tables. We use ETS tables heavily for out-of-proc caching. In message queues, in Erlang, processes communicate via messaging, sending messages, asynchronous messages to each other, and each process has a mailbox where incoming messages can be queued up. So subbinaries can sit there and reference a larger portion of data. And also, it turns out they can be also in driver queues. We didn't see these two problems in our system, but it's good to know. So keep that in mind when building your system. So if you have high traffic application, you may actually, and some slow like downstream, you can be get bottlenecked on memory really quickly. So then the solution to that problem is to call binary copy. This function was introduced, I believe, in R14. And it works really well. It can copy any binary, but also a subbinary. If you have a subbinary, it creates a takes that slice and creates a new object out of it. Now, for more complicated terms, you can do this. And it feels, so if you have like a complicated Erlang term that you know holds some sub-binaries, you can do this transformation. This is a native serialization, basically converting any Erlang term to a binary and then back. And it actually really, really fast. So you of course need to measure, and it also depends on the complexity of your term, but this trick works. So if you don't, if you have a complicated Erlang term like nesting, lots of nesting, and binary and sub-binaries are actually somewhere like leaves in that nested Erlang terms, and you don't want to like iterate over that term and meticulously copy sub-binary fields. It's doable. You can write an easy cycle. It's probably would be like 15 lines of code in Erlang, but I was lazy. I did that, and it. The end of processing of the final term. It's actually, so what we pass here as input is a serialization, deserialized protocol buffers. So because the library doesn't support copying sub-binaries natively, so we kind of wrap deserialization in that transformation, and it works automatically. So that took us maybe a couple of days to chase. The other problem, and this one is very typical. This one is very typical and very well known. It's a frequently asked questions. So if you follow, go ahead.
How does copying help with getting rid of memory leaks?
Oh, it's very simple. So when you create a copy, the larger binary that a sub-binary used to reference, it goes away. It gets immediately garbage collected because the sub-binary is no longer references it because it's actually now a new binary. It's a new object. Remember, sub-binary is a reference to a binary, and binaries are reference counted. Yes?
Why are you calling it leak? I mean, you have like a big string, and you have a reference to a small part of it, right, somewhere, so the big string doesn't get garbage collected, right? This is what is happening.
That's right, but from our system standpoint, it's a leak. I mean, the data was leaking somewhere. It's not strictly speaking a leak because Erlang is a managed environment, and in theory, you shouldn't get any like memory leaks, like.
You can get real memory leaks, you know, if you allocate memory in a driver and not free.
No, I'm not talking about that. If you never go to drivers and your application stays fully in Erlang, that's our case, then you shouldn't have that problem. Strictly speaking, you're right. I was just describing it from the point of like behavior of our application. It's
Why would you consider that a problem if it's now using more memory than it needs to be?
It's consuming more memory, and actually, in the end, after running it for a while, you will just run out of memory. It will consume all of it if you don't take care of it. So, and that's one of the things that I said. If we had very few clients running, we wouldn't have noticed that problem at all, because yeah, there is a high chance they wouldn't have ever noticed that because it wouldn't be considerable. How much time do I have? 6 minutes. Okay, great. So this is actually a frequently asked question. If you use supervision trees and you use Supervisor, the component is called pattern called Supervisor, there is a chance your system will go down very quickly. So basically, what you're using, like your OTP textbook, that's great. You expect it to work reliably and handle failures, but it turns out there's and it's a very frequent pattern in server and server environment. For example, and I'll explain it how it looks like. Basically, you start getting, Supervisor has a parameter that specifies the maximum frequency failure of one of its child. If one of its child dies at a higher frequency, keeps dying at a higher frequency, and Supervisor restarts it immediately. So if it goes into this restart loop, any frequency that you specify, like reasonable, like 1,000 deaths in a second, can be exceeded. For example, if you getting 4,000 incoming requests, and you will die less than a second, and you specify frequency like 1,000 deaths a second, you will die really quickly. So, and there is a typical solution to that problem. Unfortunately, you need to do something extra, and even if you know about that, I knew about that, you kind of can forget it to do that in some place, and then your application will die. And of course, if your top-level supervisor dies, your application dies, and when your top-level application dies, your node dies. And then, good thing it is restarted by the heartbeat, but it's not a good thing because you lose all your caches and everything. So one solution is Supervisor 2, is a modified version of OTP Supervisor written by RabbitMQ guys. So you can just rip it out from their implementation and start using it. It has an additional parameter, which is a delay, an additional delay between restarts. And that's as simple as that. Or you can introduce delay in your gen server function handlers explicitly like that. But it can get very tedious, and you need to remember to do it all the time. Sorry? You can add a startup delay. That would be another way to do that. But it would be great to have that as a part of OTP. So very simple problem has very straightforward solution. Not many people who start using Erlang know that. And even experienced users can forget and get problems. So this problem is really, really serious. So we use GenUDP. And we hit that problem twice. Once with logging. We offload our server logs by UDP, using UDP from Erlang VM. And once with application metrics, as I said, we use Graphite and statsd. So we also send log. And if you generate, and you apply your typical, OTP scenario. And what you do, you create a gen server. So first you send your logs, for example, or application metrics to a gen server, and then gen server sends them over UDP. And if your system is loaded enough, you will die. So if you use GenTCP and GenServer, and the same problem exists with GenTCP as well. So you will hit that with GenTCP. And it looks like this. So request rate goes up. I'm sorry you can't see that, but this is request rate going up, and all of a sudden it drops. So no requests coming out at all. This is actually response rate, not request rate. Requests may still come in, but we measure response rate, and that just stops. And when you look at from the other angle at what's going on in your application, and you see that in the error logger, Q stays at about like over 15,000 elements, which means it cannot offload all that logs fast enough over UDP. And you think, what the hell is going on? UDP is meant to be like really fast. There's literally shouldn't be any bottlenecks there. Well, it turns out, and it comes down to how things are implemented in Erlang. So GenServer that sends logs over UDP has an incoming message queue. And so basically logs keep coming. And then it tries to send it asynchronously over UDP, but that asynchronous call has a selective receive underneath. And this is a selective receive. And normally it's a linear operation, linear to the number of messages that's sitting in your mailbox, incoming message queue. So it actually goes over each element of the message queue until it finds a matching message. And it does that on every send attempt. And the longer your message queue becomes, the longer this operation takes. And eventually you get to the point that you just completely blocked. And the reason that why the whole system stalls is because every single process sends log messages. And every single process gets blocked by sending message to another, to your John server, which just cannot do like anything. And Erlang VM has a property that the sending processes get penalized and get preempted and not scheduled if they attempt to send a message to a process with a really long message queue. So your whole system stops. And what you see on your CPU usage graph is that there's only one core that's that's basically Erlang VM consumes only one core and nothing else happening. That was really fun. And as I said, we hit that problem twice. So the solution is, one solution is to use GenServer 2. That's again written by RabbitMQ guys. And it helps to, and it basically what it does, it drains your GenServer message queue. As soon as it receives a message, it just puts them into a like separate queue managed by itself. That's a simple solution. But we ended up doing this. So we ended up removing that synchronous call and removing that internal receive statement. And basically, instead of going through that receive cycle, we ignore the response from the driver, from the UDP driver, and just keep sending them commands. But that's not trivial, right? So, and I didn't know about this solution as well. So, but fortunately, one of our colleagues, one of my colleagues did. And of course, you can fix gen UDP. So there was a fix that turns the linear lookup into a constant time lookup when you do a selective receive, and it's already fixed in GenServer call. But I don't see any reason, like off the top of my head, why it cannot be solved for Gen TCP and Gen UDP so that users don't have to go through this headache. So last problem, client-side latencies. And remember I told you in the beginning that Erlang is really nice because you don't have to limit concurrency in your system by default. And it's true with one caveat. And it is, when your system becomes overloaded and bottlenecked on CPU, and that can happen in our system because we do some data processing, we process like incoming logs and stuff. When things get really tight in your real-time environment with lots of processes trying to do things concurrently, your communication with other services, you start experiencing client-side, really high client-side latencies when communicating to other services. In this example, and you need to look here, the blue line, and you can barely see that, it's the server-side latency, but this is client-side latency. And you can see it on this graph, but request rate was really high at this time, like 4,000 requests per second, and the Erlang node was consuming all CPU. And what happens, and we used HTTP client, and not a standard one that just doesn't work at all. So, but still, so what happens is that and Erlang tries really hard to give soft real-time, characteristic, and means it starts preempting your HTTP client. And it keeps like doing that and delaying scheduling your HTTP client and maybe some asynchronous stuff inside the Erlang VM for like, you get terrible delays. You can see it here, but this is 100 milliseconds. So the server actually responds in 2 milliseconds, but the client, all in all, gets response back in 100 milliseconds. And that's a 50% percentile, which is just crazy. So this is the same graph at 90% percentile, and this is 99 percentile, and this is maximum. And it's interesting that when you get to measuring maximum latencies, those two graphs, server-side latencies and client-side, they converge. I cannot really explain that, but so that's one thing to watch out. So when people try to think like whether we should limit concurrency, like by implementing worker pools, you should consider that. So all in all, like Erlang has been a great tool for us, for alert logic and for this project in particular. And it's been very efficient, provided that you know these tools. And some of the things that I told you about, they're well known, but not so well known and not so well explained, especially for new Erlang users. So it's a Erlang. I'll go quickly over this list. So we have thousands of concurrent processes running, and overall we're doing fine with that. Erlang is a simple and very powerful language that helps you to focus on your logic instead of like fighting with some low-level stuff. It offers really a good fault tolerance model. If you do it correctly, it actually works. So process crashes is something that you need to look at, but you can safely like ignore it. Won't wake you up in the middle of the night. The runtime and the VM is really, really stable. Like you can 100% rely on it. It's been around for over a decade. It offers rich troubleshooting capabilities. You can log into remote shell and run some commands on a production node for troubleshooting and stuff. You can also use tracing, which is also nice. And if you're smart and you know what you're doing, you can even run profiling. Other environments also offer that capabilities, but Erlang does as well. And the community is growing. It's constantly getting better. One thing I wanted to mention is rebar. So we use rebar releases, and we even started using rebar for other stuff, not Erlang, for tracking non-Erlang dependencies. And finally, there's also room for improvement. And I have a dream after using Erlang for 5 years. So I know how to deal with these problems that I talked about. Some of them were new for me, but we solved all of them really quickly. So, and the dream has a name of open server platform as opposed to open telecom platform. So some of the things that I talked about wouldn't have happened if they were addressed either as a part of OTP principles or slightly modified OTP principles, better suited for server environments. Packaging and deployment, like rebar packages, work. However, there's some legacy stuff like rel tool config. It's a mess. Like ideally, you don't want to like touch it. You want to standardize on some parameters and never see it again. So there's some legacy tools that made a lot of sense in the 90s for embedded environment and telecom. It doesn't make any sense in server environment. Logging. It's getting better. There's some good open source packages, but especially for new users, it's a mess. So the ideal setup would be an option to log to syslog or standard error, never log to files. And you need to include SASL logs properly formatted that don't blow up your VM by default. So HTTP client that works. The standard HTTP clients never use it. It's buggy and it's slow. We ended up using LHTTPC, but it's not really good as well. So we'll be migrating off of that as well. So it's actually, I don't know any HTTP client that may work for us and help to bring these latencies down. I have not. I looked at it. I think they're pretty much all the same. It comes down that their connection pools are implemented inefficiently. And there's a philosophical questions: how many like cores and how many load do you need in terms of like trying to make many requests before your connection pool implementation becomes a bottleneck? So the more kind of things that bottleneck on that single connection pool, it's another complete story. But you need to watch out for those bottlenecks and try not to overload your connection pools or implement them in a more efficient way. So this would be really nice. I don't have this is totally achievable, right? This one I don't know. Somebody just needs to care about that. So every time there's a fork hell There's in-house maintained like forks for those databases, but it's not really manageable. It's somebody needs to just fix that. And this is a stretch goal, of course. We don't use distributed Erlang, and we very consciously don't use it, because there are so many bottlenecks associated and the trickiness associated with that. Like, we avoided half of the boundary problems. Cliff Moon gave a talk yesterday. We didn't have half of these problems because we don't use distributed Erlang. We have a natural flow control across our system, end to end, so we don't have to limit anything. And so distributed Erlang is the default one. I think we have applications for that. We use it in other parts of the system, but we decided not to use it here and structure our application differently so that we don't have to use it. But it would be really nice to have reliable cluster management, leader election, distributed logging, and things like that without dealing with some of the limitations of the existing implementation. That's all I had. Any questions? Do we have time for questions? So you should have listened. It's not bad, but you should have listened about lots of limitation that it has. You can go and watch the recording of Cliff Moon's talk yesterday's, and there were also a bunch of other speakers, like from last year, Cloudant, Adam Kokolowski, I think his name. He also gave, they use distributed Erlang big time, and they hit a lot of limitations with it, and he spoke. I'm not very, I'm not the best person to answer that. I know some things, and I know some other things that make me not use it, if possible.